Hello everyone, welcome back to our Calculus 2 course. For this week lectures, I'm gonna be talking about two sections, 7.4 and 7.5. Again, we'll be talking about all about the integration techniques in this chapter. So let's start with 7.4, the integration of rational function. 7.4, integration rational function. Okay. So actually, when you guys learn the technique of integration of rational function, it's going to involve a lot of other problems that we learned before. So we gotta walk step by step. First of all, what is a rational function? Say a rational function f of x is rational ratio, a fraction of a polynomial over another polynomial. Okay? So you have a fraction of polynomial over polynomial, we're going to call a rational function. So what is a polynomial? Actually, we should learn that already. College algebra and recalc, something like this. 2x squared minus 7x plus 1. This is called polynomial, right? Actually, it's quadratic. Okay? And you have degree 3, degree 4. Okay. Then say over something like x plus 2, for example. So in here is a rational function of polynomial degree 2 over a polynomial of degree 1. And this is just an example. Okay? We have a lot of rational functions. And our job today is to learn how to integrate such a thing like this. Any degree. Okay. So there are a couple of things that you're going to know about the fraction in general, rational function. We have two types, proper fraction or improper. Proper fraction means what? The numerator is smaller than the denominator. In here we are talking about the proper fraction in terms of the degree. So this is actually an improper because what? This is a degree 2 for numerator. And then this is degree 1 denominator. Even if it's the same degree, we still call this improper. Okay? So we can have some proper function like the reciprocal of this. X plus 2 over 3x squared minus 2x plus 1. Or something like that. This, see, the top now is degree 1. The bottom is degree 2. This one is a proper fraction. Proper. Okay? And this is improper. Even if you have something like this, it's still improper. Okay? We need the numerator, the degree of the numerator strictly smaller than the degree of the denominator. And that is proper. Okay? So, to deal with this type of fraction, we always go down to proper fraction. You know why? If it's improper, then we can do what? Long division. We're going to have a polynomial as a quotient and plus a proper fraction. Let me try to explain it to you via this example. Say if I got a rational function like this, right? And of course, this one is improper. So what can I do? Since the numerator is bigger, it's got a larger degree, bigger degree in the denominator, I can always do a long division. So, okay, it's a good chance to do long division in here as well. So I got what? 2x squared minus 7x plus 1 divided by x plus 2. I take the leading term 2x squared divided by x plus 2. I got 2x. Multiply the back. 2x times x is 2x squared. 2x times 2 is plus 4x. Now I do a subtraction. This is 0. Negative 7x minus 4x is negative 11x. And add 1 right here. Negative 11x divided by x is negative 11. And multiply the back. Negative 11x. Negative 11 times 2 is negative 22. Do a subtraction. I got 23 right here. This is 0. Because 1 minus negative 22 is 23. So this is no more than the integral of 2x minus 11 then plus 23 over x plus 2 dx. Okay? The first part right here, this is the quotient that you have from your long division. So it's just a polynomial. It's always solvable easily. So it doesn't matter what integration of a rational function, you can always bring it down to the integration of a polynomial plus the integration of a proper rational function. Okay, so we can always talk about this. And so in general, we are looking for the integral of a proper fraction, a proper rational function. Okay. And we have to use a technique that I bet all of you did learn already in pre-calculus called partial fraction decomposition. Partial fraction, so T. It's a C. Fraction decomposition. What does it mean? The idea is that we try to break a big fraction out into the sum of smaller fractions, then we can integrate a little thing at a time. So say you have a fraction. Let me just give you a very general example, okay? Say I got 2x plus 3 over x plus 1 cubed times x squared plus 2 raised to the second power. Okay. Another thing about algebra you guys should know as well. Whenever you guys have polynomial of real coefficients, polynomial is 3x squared minus 7x plus 1. Those numbers 3, negative 7, 1 called the coefficients. Okay. If those numbers are real, then I claim that you can always factor the polynomial out into products of linear factors or quadratic factor up to some multiplicity. So you got like 7x to the 5th minus 6x to the 4 plus 2x cubed minus 5x squared plus 1x minus 2. This is a polynomial degree 5, right? And I don't know how, but for sure we can factor this out into a product of some linear factors or quadratic factor, and that's what we learned pre-calc already. Okay, so to make it easy in Calc 2, most of the time your exercises in the book are gonna factor out for you already. If not, they're gonna give you a very easy number, and then you know how to factor. And you know that for sure, whenever you have a polynomial, you can always factor out into linear and quadratic factors if the coefficients are all real numbers. And if it's complex number, you can factor out all to linear, but we always talk about real numbers in Calc 2. So, linear or quadratic, okay? And the rule for breaking out is we're looking at breaking this out is this. We're looking at the factors in the denominator, okay? So I see that in this example, I give you two typical types of factors in here. This one is a linear one, just a single x, right? And plus a constant, of course, raised to some power. It's called the multiplicity. And then the second type of factor is what a quadratic one, right? Quadratic, x squared plus 2. Okay? By the way, say if you have a quadratic like x squared minus 4, and I claim that actually is factorable. This one is just x minus 2 times x plus 2, right? And then it's come to linear. With something like this, x squared plus 2, in terms of real numbers, I cannot factor this out anymore. It's called irreducible. Okay? Cannot break down anymore. I have to leave it as quadratic, x squared plus 2, and have to deal with it. Okay, and this is how we decompose this fraction. We start with the first factor in here. I got what? X plus 1, right? That's a factor. Then this is linear, it's proper fraction, so this is degree 1. So the numerator is gotta be degree 0, less than 1, so it's gotta be a constant. So I call it A. And then we can have another fraction, it's still linear on the bottom, but now it's multiplicity 2. Or it could be multiplicity 3, third power. And this kind of review from pre-calc, so I can go kind of quick. And again, it's just constant, so B and C. And then for quadratic, same idea. I got x squared plus 2 as the possible denominator for the second factor right here, but this is quadratic, degree 2. So the numerator could be of degree 1. So what? Bx, B plus E, and then you write all the possible multiplicity in here. I got x squared plus 2, and E, and then fx, g, and you have to solve for A, B, C, D, E, F, G, and you have a bunch of fractions. So in Calc 2, you want to integrate this integral. You can break it out to 1, 2, 3, 4, 5 partial fraction, and then you can integrate one fraction at a time. Okay? And of course, this is way too big. I'm just trying to give you an example of the idea how to decompose a big fraction. But all the exercises in your textbook are going to be much simpler and smaller. So we have to use some technique that we learned previously in pre-calc. Partial fraction decomposition, and then you have to solve all the numbers on the numerator first. Okay? And when we get to the exercises, I will show you how. Recall you that. Okay? So anyway, any problems of integration of rational function can be nailed down to integration of a proper fraction, right? Proper rational function. And how to deal with this? We have to decompose. Only proper fraction can be decomposed that way. Okay, if it's not proper, yeah, we have to do long division, and we have the a polynomial as a quotient, and then a proper fraction, and we can decompose. Okay, let's see. All right, so in here the rational function can always decompose that, and then the problem there is what we have to look for the integration of those things. So let me just show you the typical integration that you guys are going to need for this section. The first one is the integral of 1 over x plus 1 dx. Of course, it's any constant. I'll just write 1 in here. Okay? And this one going to be equal to ln of x plus 1 plus c. The key is let u equal to x plus 1. Then du equal to dx. So this problem becomes 1 over u du. Okay? And then you may have a multiplicity of x plus 1, so you can look for integral of 1 over x plus 1 raised to some power. I'll just make it up to power 3. 4, 5 is the same way, dx. Dx, I say. And for this type of problem, you're going to do another u sub, I think. But let's rewrite it first. This is the same thing as integral of x plus 1 raised to the negative 3 dx. Still let u equal to 1 plus x. U equal to x plus 1 or 1 plus x, the same thing. So this is integral of u to negative 3 dx is du. And you know how to solve for this one, same way. But this is going to use the power rule. This is going to be the log. Okay? So if you have a linear factor on the denominator, it's piece of cake. Just do a u sub, and you should be able to take care of the problem. Next, we have to use the integration with quadratic factor. So I'm going to use x squared plus 1 as an example in this type of fraction. Okay? So this one right here, actually we have a formula. This is tangent inverse, I think. Tangent inverse of x dx. So what if you have something like 1 over x squared plus 2? And you have to modify it, make it look like x squared plus 1, I think. So divide the bottom by 2, divide the top by 2, right? So this multiply 1/2 on the top and divide the bottom by 2, divide the bottom by 2. Right? Multiply the top and the bottom by 1/2. It's the same thing, right? The idea is you have number 1 right here. So this is no more than 1 over x over square root of 2 squared plus 1 dx, and you let u equal to 1 over, u equal to x over square root of 2. And let u equal to x over square root of 2. You bring back to this problem and you can solve. Okay? There is another problem that you may see in this quadratic. Dealing with quadratic is harder. Say you have something like this. Integral of 1 over x squared, say, plus 2x plus 3. See? This is quadratic, still irreducible, I think. Is that right? Yeah. dx. And we have to use a technique that we already learned a long time ago in college algebra and pre-calc, something called completely square. Completely square. Okay, quadratic. So we're going to make it like a perfect square plus a constant. So x squared plus 2x plus 3 can be rewritten as x squared plus 2x plus 1 and then plus 2. And this is what? X plus 1 squared plus 2. Okay? So this integral is no more than the integral of 1 over x squared, x plus 1 squared and plus 2 dx. Alright, and then you do a u sub for x plus 1, you're going to have 1 over u squared plus 2 du. Let's come back to the previous problem. Okay, so this completed square technique is going to be useful as well. But anyway, this is not the hardest one yet. Then what if you have multiplicity for x squared plus 1? Say I got to the third power. And I claim that since this is harder, I don't see any exercise in the book that they have it. But in reality, you may see a problem like this because I hope many of you guys are going to move on and learn more about this stuff. So this one is another type. And the key is what we have to do trig sub in here. Okay? We have multiplicity. We have to do trig sub. I'll let x equal to tangent theta. You guys see why I do this trig sub? Because it's x squared plus 1. It's going to be tangent squared plus 1. And if you know some trig identity, you know that tangent square plus 1 is equal to secant square. Okay? And now is what? Dx equal to secant square theta d theta. So this problem will become what? Dx is secant square theta d theta. And say the bottom right here. X squared plus 1 is tangent square plus 1. Tangent square theta plus 1, and then raised to the third power. Tangent square plus 1 is secant square. Secant square raised to the third power is secant to the 6th. This is secant square theta over secant to the 6th theta d theta. You can simplify. This is integral 1 over secant to the 4th theta d theta. And not done yet. Secant to the 4 converted back to cosine. The reciprocal of secant is cosine. So this is cosine to the 4 theta d theta. Now what? We have to do what? The double angle formula or half angle formula, whatever you call it. You know that cosine square theta is 1 plus cosine of 2 theta over 2. So this one will become integral. Cosine to the 4 is cosine square theta, everything square, right? This is cosine to the 4. So this is 1 plus cosine 2 theta over 2. Everything square d theta. Now you have to follow that out, and you apply the double angle formula again, and you can integrate. You see how much work if you have quadratic with multiplicity. And I guess that's why I wouldn't give you any exercises of it. But just in case you want to use this, you know where to look at. Okay, now let me go back to some example. I'll show you how to do partial decomposition, and then we're going to do the integration of the partial fractions. Okay, let's take a look at some examples. Okay, start with something easy. I see this one. Integral of 4 plus x over 1 plus 2x times 3 minus x dx. Alright, so this fraction is already proper because the numerator is a polynomial of degree 1, it's a linear one. Whereas the bottom, the denominator is a polynomial of degree 2, right? A linear times linear is quadratic. So, and they even factor out for you. It's a linear times a linear. So we want to deal with this type of problem. I think I forgot something. One more problem before we get in here. Sorry, let me add it to our list. Okay, you may see this type of problem as well. Say x over x squared plus 1 dx. But this is easy for you guys to do. Let u equal to x squared plus 1. Then you have du is 2x dx. You plug it in, you have the answer. Okay? And it's also easy if you have this raised to any exponent. Say 3. You still do the same thing. Okay? You plug it in, you have the answer. So shouldn't be too hard. And I apologize that I forgot to mention this case. I just talk about constant, but this is quadratic, so it could be an x on top as well. Alright? But this is going to be taken care of easily. Let's go back to our problem. So we have to decompose the fraction. I got 4 plus x over 1 plus 2x times 3 minus x, okay? And if I decompose this, I should have two denominator. The first one going to be 1 plus 2x, and the second one going to be 3 minus x. They're both linear with multiplicity 1. See, no exponent, so that's simple, right? The denominator is linear, so the numerator is just going to be a constant. And we have to solve for just two constants, a and b. All right? How do you solve a and b in here? I'll do the quick way that I can usually think of. If I have fraction on the left equal to fraction on the right, then if I make the two denominator on both sides the same, then the numerator is going to be the same, right? The numerator is going to be equal to each other. In other words, if I multiply this fraction by 3 minus x, and I multiply this fraction by 1 plus 2x, of course I have to do the same thing for numerator, 3 minus x, then all fractions have the same denominator, and the numerator on the left going to be 4 plus x, going to be equal to a times 3 minus x plus b times 1 plus 2x. I should not use the word equal, it should be identical, okay? The linear polynomial on the left going to be identical to the linear polynomial on the right, okay? And that means what? If you use our canonical method, you're going to multiply them all out, combine the line terms, back to pre-calc. I claim it's a little bit long. So let's do the shortcut in here. This is true for all x. We can plug in any value for x. And I'm going to choose x equal to 3, plug in first. You see why? Because when I plug in x equal to 3, the a is going to cancel out, right? Try x equal to 3. I hope I can solve a and b. X equal to 3, the right hand side is 7. I'm sorry, the left hand side is 7. Right hand side, that's 3 minus 3 is 0, so no a. 3 right here, x is 3, 2x is 6 plus 1 is 7, so 7b. So I can solve for b quickly. B is equal to 1. See? We don't have a lot of time to go over all of those because we have to deal with integration as well to try to solve decompose a fraction, solve a and b as quick as possible. And similarly, I can plug in any other value and then solve. We have b already, and then I plug in any other value for x and solve for a. You can plug in what? X equal to negative 1/2. You see why? Negative 1/2 times 2 is negative 1 plus 1, going to be 0. But I don't like fractions, so I can try any other value. Say try x equal to 0. Okay. So if x equals 0, I got what? 4 is equal to 3a, 0 right here, so plus b, which is 3a plus 1. And I can solve a from here. I got 3 is equal to 3a, so of course a is also equal to 1. So what do we have in here? We have that a is 1 and b is 1, so if you decompose that fraction, you're going to have 1 over 1 plus 2x and 1 over 3 minus x. So this rational functions will becomes 1 over 1 plus 2x dx plus integral of 1 over 3 minus x dx. And now those things you can integrate easily. And the hint is use up, right? You let u equal to the denominator. Let u equal to 1 plus 2f. So du is 2 times dx. This one right here, you let, I want to use different letters. So let v equal to 3 minus x. So dv is negative dx. This one becomes 1 over u. dx is 1/2 du. And this one is 1 over v, right? And dx is negative dv, right? So this is 1/2 ln of u, which is ln of 1 plus 2x, minus ln of v, which is ln of 3 minus x, and then plus c. See, you have the answer. So you see, even though it's just one section, we talk about integration of rational function, but we are including a lot of things in here. Integration of what? Polynomial, fraction with linear factor, and then quadratic factor, and then tangent inverse, and then trig sub, okay? And then we have to use the fraction decomposition techniques that we learned previously in pre-calc. And then what else? We have to use the completed square techniques. Of course, not all the techniques are going to be used in one problem, but you guys really need to know a lot of things to get to this section. Okay, so let me show you a couple more examples before I move on. We got the easiest one already. Try some other examples. It's trickier. Okay, I see this one. Integral of